So, good afternoon, everyone. Welcome to the AstroAI lunch seminar. Today, I'm happy to introduce someone I actually just met in person for the first time, even though we tried to bring you last semester. Noah Wolfe, who's a fourth-year grad student at MIT, working in the group of Salvo Vitale on gravitational-wave astrophysics. And, as data grows about gravitational-wave events, Noah has been working on Bayesian statistics and how to update, physics from these systems sort of on the fly as new data comes and how that helps on the characterization of the populations leading to gravitational wave mergers. So the floor is yours. Please interrupt with question anytime, and you have the full blog, so take it easy and enjoy. Thank you. All right. And please do the sign up for attendance. Thank you.
Yeah, no, thank you again for that introduction, and thanks you all for having me. I don't think I've met too many folks in this room, but I'm really excited to be here. Actually, Anna Sophia was the one who originally invited me. I don't think she could be here today. In any case, yeah, feel free to interrupt with questions at any point. The work I'm going to be talking about today is on the archive, thankfully, finally, and you can find it at that QR code or that phone number up in the top right. This is some work that I've done with my advisor, Salvo Vitale, as well as collaborators at the University of Nottingham in Glasgow. And of course, I have to acknowledge the really generous support of the NSF, both supporting LIGO as a whole, as well as my GRFP, and IFI down at MIT, which is how I got all the nice compute, which is at, funnily enough, a Harvard domain. So thanks to Harvard too, I guess. Yeah, in any case.
I'm trying to get rid of that sign there.
Oh, yeah. It won't let me see my mouse, so 1 second.
Sorry.
No.
Maybe I'm making it worse. Sometimes
Oops.
hitting escape for a second.
Yeah, there we go. Sorry, y'all. Okay, I'm gonna try to share again.
It's better.
Okay, now I just need to share it. Okay, share, hide all this. Okay,
yeah,
we're in business. All right. So today I'd like to talk about a couple things to give you a sense of how I'd like to structure my talk today. First, I'm just going to motivate broadly gravitational wave astronomy, since I don't think most folks in this room think about gravitational wave astronomy on a daily basis. I'm going to try and motivate the specific work I did that Raphael briefly alluded to. We expect to have a really large volume of gravitational wave data in the future, which is exciting. We'll be able to probe a lot of interesting new astrophysics, but it's also kind of terrifying, imagining actually sitting down and analyzing all those data. The particular method we'll use to approach this challenge is we're going to actually operationalize a Bayesian update using neural variational inference. We're going to apply that method to real and simulated data, and I'll also conclude, summarize, and make some notes on what else this kind of Bayesian updating framework gives us. So to establish some preliminaries, and the lingo I use when I think about a black hole binary, the kind of primary source class in our gravitational wave data sets right now, black holes, as you probably know, are extremely simple objects, right? So I just need the mass of each black hole as well as the spin vector. And so I have 8 intrinsic parameters of the black hole binary that characterize this system. This is assuming it's circular. You can add on a few more if it's eccentric. But for what I'm talking about today, I'm mostly interested in the mass, the primary mass of the heavier object, the secondary mass of the lighter object, and their spin vectors. And really, there's 2 numbers for those spin vectors we care about: the dimensionless magnitude of each spin vector. It's just the magnitude non-dimensionalized with the appropriate factors of g and c and the black hole mass, as well as this tilt angle tau, which is the angle between the vector of the black hole spin and the orbital angular momentum. Right, so those are the parameters that we chiefly try and measure with gravitational waves and that characterize our black hole binaries. If you're trolling around the gravitational wave literature at all, you'll also see reference to 7 extrinsic parameters that characterize the location and orientation of the binary relative to our detectors. But we won't see those for the rest of this talk. And so just to broadly motivate, like, why gravitational wave astronomy at all, like not just because it's cool, even though it is extremely cool. Gravitational wave observations are going to have systematic uncertainties, which are a lot different than the systematic uncertainties in like traditional electromagnetic astronomy. So if I want to probe high energy astrophysical phenomena, now I have two kind of independent ways to do that. So that's exciting and valuable in its own right. When we study the mergers of black hole binaries in particular, we can do a number of things. We can perform tests of general relativity in the strong field and high velocity regime. We can measure cosmic expansion history. If one or both of these objects is a neutron star, we can start to probe nuclear matter at extreme densities. And the thing that I've spent most of my PhD thinking about is we could also potentially identify the astrophysical channels by which these black hole binaries are formed. To give you a brief sense of how we think about this from the theoretical perspective, you can broadly divide, these formation channels into two categories. So on the left, we have formation of these binaries in isolation, in the field of the galaxy. You might have two massive stars that co-evolve, essentially unperturbed by any other stars or anything else around them. We think that these systems, will need to have mass transfer to harden the binary so that it merges within a Hubble time. We also think that these systems will have typically lighter black holes, and they'll have smaller and typically orbit-aligned spins. On the other hand, if you imagine forming your black hole binary in a dense dynamical environment like a globular cluster, we think that that formation channel or that class of formation channels will tend to give us heavier black holes with larger and randomly oriented spins. More about some of the theoretical perspective if you're interested, but more to say that we think there are, some broad formation, like classes of formation channels for forming these binaries, and we think that we can identify them based on the mass and the spins of the observed mergers. But in general, right, all of those questions that we can ask of individual black hole binaries, right, testing general relativity to identifying astrophysical formation, well, we can ask all of those questions of their population as well. And so that's what I spend a lot of my time working on day to day, are these kinds of gravitational wave population analyses. So we'll get into more of the details later, but just to kind of, again, sketch out what this looks like, I'm showing one plot from the LVK's LIGO-Virgo-Kagra collaboration's analysis of the latest public catalog. And here what I'm plotting on the y-axis is the differential merger rate of black holes in the universe as a function of that primary mass of the system. This plot not only accounts for what we observed, but also our understanding of the selection effects of the detector, right? We don't actually detect every black hole merger in the universe, but we think we can model that really well and back that out when we try and infer the population distribution. The specific lines being shown here in orange, I'm showing the analysis with the latest public data set. The orange line is the median, and this orange shaded region is the 90% credible region. So we infer the astrophysical population with some uncertainty. But then the power of taking all of our data and putting them into a population analysis is I can start to ask questions like, what does this excess of black holes at 10 solar masses mean for stellar evolution? What does this maybe bump or knee at 35 solar masses? Does that imply some previously unknown astrophysical formation channel? And you can imagine performing the same kind of game with the population level distributions of like the spin magnitudes, for example. So I'll pause there in case anyone has any initial questions. This is mostly just to motivate what we're doing. Yeah.
So this is the rates at which a system with a primary mass of x-axis happens in the entire universe, modeled, constrained by the current data.
Yes.
Right?
Yes. So, I look at any co-moving cubic gigaparsec of space, and I say over, a year, we should have so many black holes merging with 10 solar masses or 35 solar masses.
And the difference between the two contours there, the gray and the orange, is what, just newer data, more data added?
Yes. And that specific marginal in the inset is, specifically the power law index between, like I model the population as a power law around here. versus at higher masses, and I'm comparing those two power law indices in the top right. Yeah, ask me more about the LVK's result if you're interested. I'm kind of going to move away from this now because this is mostly just to motivate, like, why do this kind of analysis that I'm doing at all? Okay. So like I said, the questions that we can ask of individual events, well, we can actually combine all those noisy data and answer those questions of their population. So fantastic. We have a framework for answering interesting scientific questions, and I think the horizon for answering those questions is really bright. We already have 3 operating gravitational wave detectors, so the 2 LIGO detectors in the United States, as well as Virgo in Italy. There is Kagra coming online in Japan, and hopefully over the next 5 or 10 years, a LIGO detector in India. Over the next decade or so, we also anticipate 2 next generation facilities, the Cosmic Explorer in the US, as well as the Einstein Telescope in Europe. These are really exciting facilities because we think, like when I look at Cosmic Explorer in particular, that we will be able to detect binary black hole mergers in roughly the mass range we just looked at, a few to a few tens of solar masses. We think we'll be able to detect such stellar mass binary black holes is essentially out to like redshift of 50 or something. We don't expect any detections there, though if we found some, it would be quite interesting for other reasons. In any case, that's to drive home the point, and let me quantify that we expect a really extreme volume of data in the future, at least extreme relative to what we have right now. So this is a plot from Floor, actually. On the y-axis, we're plotting the number of detections, and the black line is showing specifically detections of black hole mergers, which is what I'm focusing on in this talk. And the x-axis is time, right? So we're roughly here in the red line. The latest public LIGO gravitational wave dataset has 153 confident black hole mergers, or confident black hole merger detections. Okay. Over the next 5 to 10 years, we expect that number to grow anywhere from a few thousand to a few 100,000 or even million black hole mergers in our catalog. And so that's extremely exciting, right? We've discussed some of these astrophysical formation channels, and we want to try and tease them apart. And we have to do it in this, 8-dimensional space of the binary source parameters. Well, more data is going to help me do that. But I'll explain in a moment that this is also kind of terrifying. At least I don't think our current, analyses infrastructure will be able to hold up under this weight of data. And so what we want to do in this project is find a way to kind of iteratively update our understanding of black hole populations as opposed to doing it all at once. Okay. To give you a little sense of the ingredients that go into doing this kind of analysis in more detail, and again, to help motivate why I'm kind of terrified by this data volume, I'm going to get into some of the dirty details of how we do this population inference. So our goal is to combine uncertain source parameter measurements. This is broadly what we call our catalog of, say, black hole mergers. And we want to combine those uncertain source parameter measurements into a unified understanding of astrophysical population. What we have to do is we first have to assume some functional form for that astrophysical population, right? If we're being proper Bayesians about it, there's always tons of assumptions on the right-hand side of our conditional bar, and this is one of them. But I assume some functional form, the mass distribution is some composition of power laws and Gaussian peaks, for example. And my goal is to infer the parameters of that astrophysical population model, right? The indices of those power laws or the location and width of those Gaussian peaks that I assume my population is modeled as, and I'm going to call those parameters lambda. Next, what we have to do, like I said, we have to fold in our selection effects. Specifically, we do that by estimating how many sources, what I call n bar here, that we'd expect to detect if the universe were actually described by some particular set of population parameters lambda. And similarly, we have to evaluate the likelihood of each of our n observations, assuming again that the population is described by some particular set of lambda. And then you kind of rinse and repeat steps 2 and 3 in your favorite, stochastic inference algorithm, and out comes astrophysics, and specifically those population distributions we looked at a few slides ago. Right, to write this all mathematically, we have an inhomogeneous Poisson likelihood for our catalog of observations in the brackets D. We have this exponential suppression at the front, depending on the number of sources I expect to have detected. And then we have this product over the likelihood of observing each piece of data given some astrophysical population. Now, critically, right, I'm also able to make the assumption, at least with current detectors and current data sets, that our data are independent, right? If I take a black hole observed at one time, it should be independent of my observation at a later time. And in detail, right, that's because we're detecting these things on the order of like once every few days when the detectors are online. And so, you know, the signals are not overlapping, and so their likelihood should be independent. Yeah.
Is that assumption going to change as the volume of data gets bigger?
That assumption will change. In detail, it will change. So people have been studying this, however, and it looks like with at least next generation ground-based detectors that the details get kind of gross, but basically you can still treat these as independent because it doesn't change the underlying like power spectral density of the noise. That kind of you know, correlation between observations is going to be much more impactful if you look at space-based detectors like LISA. And there they have to do a global fit where they just fit everything at once. Now, the thing we show in our paper is that although we make this particular assumption for this likelihood right now, I think it should be possible to put one of these global fits where I fit all of the signals and all of the noise at once. It should still be possible to fit one of these global fit analyses into our framework. Thankfully, we're going to make this much simpler assumption for our current data. So I take this likelihood of our catalog, I invert it with Bayes' theorem, and now I get a posterior on the population parameters lambda. Okay. Now, it turns out that the cost of evaluating this likelihood is at least going to scale linearly, and I think you can see that, right, over this product of the size of my catalog. But it might scale as much as quadratically in the catalog size for some extremely technical reasons that go into how we actually estimate this likelihood on the right and that n bar there. There's still a little debate in the literature about precisely where this scaling falls, but even if it's linear and I grow my catalog by a few orders of magnitude, then my computation is going to become a few orders of magnitude more expensive. So, okay, this is to kind of motivate why I think we need to do this Bayesian updating thing and divide our catalog into smaller pieces in the first place. Just to remind you, right, we expect a few orders of magnitude growth in the catalog size on the y-axis. Okay. So, like I've alluded to, Bayesian updating or Bayesian statistics provides a really natural framework for dealing with extremely large and extremely complicated data sets because I can divide it into much smaller, much simpler pieces by analyzing one set of data and using that to inform my analysis of the next set of data, right? As James reminds us, one man's prior is another man's posterior, or really, as we flip the quote around in our paper and make it a little more gender neutral, one person's posterior is a later person's prior, right? That's the goal. Now, why have we not done this before? It's partly because our data volume has simply not been that much, right? We don't need to do it yet. But also, it's kind of, you know, the reason is encoded in this statement. I need a posterior probability that I can use as a later prior probability. The traditional output of like stochastic sampling algorithms, you know, Markov chain Monte Carlo or nested sampling, I get a bunch of discrete samples from my posterior, but I don't know what the posterior density is anywhere else in that space. And that's really what I need to be able to perform this kind of Bayesian updating. I need to be able to evaluate a data-informed prior probability. And so to kind of sketch out how we do that, and soon enough the machine learning aspect will come into this, this is this framework we call neural Bayesian updating. But basically, the idea is I start on the left, right? I have some, you know, typically uninformed prior on lambda. I say uninformed, really I mean flat. We don't usually do the smarter thing of assuming a Jeffreys prior. But, you know, this is probably a fine assumption. And in any case, it's not informed by any previous observations. So I take some uninformed prior lambda. I'm going to multiply in the likelihood of some first set of data, D1, multiply that by my uninformed prior, and then I'm going to get out a posterior, which I've sketched out in blue. But what I'm going to do is, in this work, I'm going to use a density estimator for that posterior. Specifically, we use variational inference. I'll talk a little bit more about what that is in a moment, but this is an inference technique that naturally gives us not only samples from the posterior, but a posterior density estimate. And I'm going to call that posterior density estimate Q, and I'm going to call it Q sub 1 posterior given the first set of data, right? So, okay, now I have an approximate posterior density. And now when I observe some next set of data, D2, I can plug that into my analysis as a data-informed prior. So what I've done up here is I've again written the likelihood. I can factorize it because I can, for now, treat them as independent of time. I have the likelihood of this new set of data, likelihood of the old set of data, and some uninformed prior. I can rewrite this like this old data likelihood times prior in terms of my posterior density estimator. And then I can approximate that whole thing with another posterior density estimator, Q2. And imagine continuing on ad infinitum or ad nauseum, depending on what you think. And so, okay, great. Now, something we're worried about, and I can comment on this more after, is, does error accumulate as I'm doing these multiple stages of approximation? Oh, yes.
Yeah. Does D2 include D1?
No. No.
No.
Yeah. That's why we're able to nicely separate this like this. Yeah, something in principle we're worried about as well. And to kind of drive home the point, we do multiple stages of approximation here. So I essentially learn an approximate data informed prior, and then I fit this times some likelihood with another approximation. And so in principle, we're worried about error accumulating with these multiple stages of approximation. I'll comment more in a moment, but we do try and track this accumulation of error through subsequent stages of the Bayesian update. So I mentioned we use variational inference. In principle, that's not the only tool I could use, right? I could imagine, performing the analysis, the Bayesian analysis with some kind of more traditional algorithm, right? I could run my nested sampling. I could get out a number of discrete samples from the posterior, and I could fit that with, choose your favorite, a KDE, a Gaussian mixture model, whatever. You could also imagine, and some people have done this in a slightly different context, performing some kind of simulation-based inference, learning a density estimator conditioned on some observed catalog. But in a recent paper, a little bit before this, led by a former postdoc in the LIGO lab at MIT, we actually found that variational inference for a particular class of population inference problems was extremely fast, right? So with nested sampling, it can take minutes to hours to perform these analyses, and we can do the same thing in basically a minute with variational inference. And so we said, okay, that's pretty cool. Let's use this nice and speedy tool to perform this Bayesian updating thing. But in principle, you don't need to use specifically this tool. Okay. Just in case you're unaware, but I suspect this audience is pretty aware, right? Variational inference, I'm approximating my population posterior with a normalizing flow, specifically, or a normalizing flow, which is a learnable bijection from some simple density to the posterior, right? So I have some unimodal Gaussian, and I can draw samples from that. I can evaluate that density pretty easy, but I want to transform to my more complicated target posterior. In this work, we specifically use a neural network as our normalizing flow, specifically the block neural autoregressive flow, which is a neural network with some extra constraints placed on it to make sure that it's bijective. Ask me more about that after if you're interested. I actually had to get pretty dirty with this, like writing my own custom Jacobian vector product because it's not analytically invertible. There's all this stuff under the hood. So if you're a super nerd, please ask me after if you're interested. To kind of sketch out, how we take this idea of a normalizing flow and actually perform inference with it, right? Variational inference in particular is going to proceed by minimizing the reverse KL divergence between my approximation to the posterior Q and my actual posterior P. This form is advantageous because I can really easily draw samples from Q, and so evaluate this as a Monte Carlo integral, and I can relatively easily evaluate the likelihood, or really the posterior on lambda, but I can't do the reverse, right? It's hard to draw samples from the posterior, so I like this form of the KL divergence. We're going to minimize this with stochastic gradient descent, and in all the experiments I show, there's been some hyperparameter tuning. Feel free to ask me if you're interested, but in principle, the ones we're most interested in tuning are going to be the learning schedule, as well as the size of the normalizing flow, how many parameters are in that block neural autoregressive transformation. And finally, one other thing we do is when I've trained my variational approximate, given the first data, Q1, I'm going to have some trained set of parameters for that represent that approximation. And now when the next data set comes in and I want to train Q2 to match this posterior given some extra data, well, I'm actually going to initialize training of Q2 with the final trained parameters of Q1. Hopefully, right, if in principle, as I add more data, my error bars stay roughly in the same place, but shrink. then, this is a pretty good approximation to where this guy should be. Yeah.
So can you quickly motivate why you do this updating procedure rather than taking the full batch of data at once? Is it just because your data is that spaced out that you want or is this just a procedure helping your network learn?
Let me make sure I understand the question. So the question is, I guess in terms of which batch of data are you referring to? Like,
So you're doing this continual learning process, right? Where you just update with new data.
Yeah.
Why not just taking the full batch of data at once?
okay. So in practice, there is some amount of batching, right? So in LIGO, what happens is there's a bunch of search pipelines constantly looking at the data, and they'll say, oh, I have a trigger. I think I detected a binary black hole merger in some particular window of data. And so that particular chunk of data, is, D2 or D1 in this. So I'm taking these particular chunks of data at a time and feeding them into this Bayesian updating procedure. Does that make sense? Does that answer your question?
Yeah, I guess, yeah.
Okay. And finally, I mentioned, we're worried about error accumulating between each stage of the update. So we not only look at the loss curve, right, make sure the loss is descending, but we also are going to evaluate what is essentially the efficiency of reweighting from my approximation to the posterior to the actual target posterior. And we're going to do that at each stage. Specifically, we use yet another form of this reweighting efficiency. We look at the Pareto shape of that importance weight distribution, which we had used in a previous paper. But essentially, this is the reweighting efficiency, right? Am I learning at least an accurate proposal distribution at each stage with the Bayesian update? Yeah.
Can you spend a minute explaining that last bullet there? What is it that you do, the Pareto shape convergence? What is it that is measuring? Why do you need it?
Yes. So this Pareto shape is essentially, like I said, it's essentially doing the same thing as a reweighting efficiency, but the difference is how this treats the tail of the importance weight distribution. That's what this Pareto shape gives us a sense of. This paper here by Vitari, they make the claim that in principle, you're able to get essentially a higher effective sample, like you're able to more efficiently reweight your distribution by treating the tails of the importance weight distribution in this way. In practice, I have found that actually you can use either the importance sampling efficiency, or you can use this and they're going to give you essentially the same answer about whether you're converged or not. This was mostly, we wanted to see if this made a meaningful improvement, and maybe my proposal distribution is not as accurate as I'd like, but I'm still able to get some fidelity on the target density. Yeah, I'm going to leave most of the technical description to that paper, but for now we can just think of this as essentially importance weighting. Yeah.
On that note,
Yeah.
have you done the test where you essentially take a problem and you do like a nested sampling, like a really brute force nested sampling, got the posterior shape, and then compared it to your variance inference?
I did that in one. Yes, I've done that in one case to try and diagnose and debug some other things. Yeah, the reason I haven't tried to do that, well, okay, I'll show results in a moment. The reason I haven't tried to do that for most of these experiments after each update is because of how expensive it gets. I've done that in one case. It seems to perform well enough. And relatedly, this seems to be a pretty good evaluator of whether or not I've converged. Though I'll also say, right, either using an actual importance reweighting efficiency or this slightly tuned up version looking at the Pareto shape, any of these metrics looking at the importance weight distribution are actually pretty conservative, especially as the dimensionality of your problem gets higher, because there's basically an exponential suppression in how well you fit the target, how well your proposal distribution works in higher dimension. So this is actually a pretty conservative metric. And so that gives us some additional sense like, okay, our results work, but I'll show you in a moment, this plot. This plot is really why I'm confident that our results work, at least for relatively low dimensional versions of this problem with current data sets. So in blue, what I'm showing is the analysis where I take the entire latest gravitational wave data set and I put it in my traditional nested sampling algorithm, and I get out the blue results. So Solid line is the median, shaded region is the 90% credible region. On the top left, I'm showing my, this is now not a rate density, but a just normalized density as a function of primary mass ratio in the top right, redshift. Now this is a differential merger rate density as a function of redshift in the bottom left, spin magnitude in the middle, and spin tilt in the bottom right. Now spin tilt, it doesn't work. I'll make a comment on why it doesn't work in a moment. For everything else, the colored lines are Bayesian updating, and they seem to match the blue pretty well. So specifically what's happening is I'm going to fit with variational inference, a density estimator to the previous catalog of gravitational wave observations. This is GWTC3, has about 69 events. I'm going to take variational inference. I'm going to fit a density estimator to the posterior given that old set of data. And then I'm going to perform Bayesian updates, folding in the entire new set of data on top of that at 3 different cadences. Right, so in orange, I take GWTC3, and then I fold in all of the latest data set at once, essentially doubling the catalog size. In green, I'm going to fold those new data in month by month, right? So this latest data set are observations from June 2023 to January 2024, and I'm going to add in all of the June 2023 data on top of the old catalog in one step, and then I'm going to add each month on top after that. And finally, in pink, I'm performing updates event by event. So I still start from the old catalog, GWTC3, and then I add on every new event in the latest observing run, one after the other as they arrived. And so that's how I get those different colored curves here. And again, in mass ratio, redshift, and spin magnitude, I think we're bang on. I think we did the right thing. In spin tilt, we have some issues. Specifically, as I increase the cadence of my updates, my fidelity to the analysis I get in the usual way gets worse. Now, if you're deep in the sauce of gravitational wave population analyses like I have been, you may know that the spin tilts are actually strongly susceptible to certain numerical variances when I evaluate that catalog likelihood, as well as Poisson variance. Another way to put that is the distribution I get out is really driven by the loudest events. On an event by event basis, I basically never measure this parameter variable. So what I think is happening is that small errors are accumulating as I perform each Bayesian update, right, because of these various stages of approximation, and that what little information may be contained on the spin tilt in each event is often washed out. Yeah.
So what does that mean for analysis of real data in the future? Would you want the community to wait until they have 10 more events before they update their posterior or I mean,
yeah. I think there's gonna be some sweet spots. So I think on the one hand, yeah, as we've shown, performing these updates with bigger batches of data tends to work better. I think on the other hand, you know, if you want to go faster, you can go faster and just say, you know, here's the caveat, maybe don't trust this particular marginal yet. I think that will, you know, precisely where the community lands is going to depend on both, you know, how good these measurements get in the future. Do they become much better? Do we actually tend to measure this one as well as everything else? It's also going to depend on what kind of astrophysical questions you want to answer. Maybe I don't care about this parameter. Maybe I just want to know the mass distribution and I want to know it right now. Fair enough. So I think it's a caveat. I think it's one we highlight. And so that's how I'd answer your question. To kind of test my hypothesis that, you know, the little bit of information that remains in many events is getting washed out, we ran a simulation study where I generated a mock catalog of gravitational wave sources, comparable in size to the number of updates I did here. In blue, again, I get the result I get when I analyze that mock catalog with nested sampling and kind of uninformed priors, the usual method. And in pink, I update event by event. And there, and in white, I'm showing the true astrophysical distribution I used for my simulation study. Now here, we're getting the right answer. And so I think this validates a little more this hypothesis that there's some small amount of information that's getting washed out, as opposed to when I use many loud and typically more informative sources. Yeah.
You say nested sampling there, that's nested sampling of the 54 times 8-dimensional space or.
Yeah, no, so nested sampling here is in the space of the population parameters lambda. And so my control over the population parameters lambda, like the dimensionality of that, comes in with the functional form I assume. So like, for example, when I'm analyzing tilt, it's a very simple functional form. I assume it's a mixture of an isotropic and a truncated Gaussian distribution. So I have a mixing fraction, location, and scale. So I have 3 parameters from this. And I have, order 10 other parameters when I account from how I model the other marginal source parameters. And so here I'm performing this variational inference and this Bayesian updating in I think it's like 15-dimensional space. Now, I'll show in a moment, if we have time, doing the same thing in 100-dimensional space. But briefly, just to flash one exciting thing we can do with this method as well. So I mentioned that I perform these updates month by month, as well as event by event. And so I can show you posteriors after each month and after each event. So on the x-axis, I'm showing the spin magnitude, my black hole spin magnitude, and on the y-axis, my normalized population density and spin magnitude. And here, the purple line, I'm just showing the 90% credible region. I've left out the median. And this purple is after GWTC3, that old catalog, and then I add in 1 month of the new data set. I can then add in successive months, right? I can add July, August, September, October. Okay, our error bars are slowly but surely shrinking. That makes sense. And then something happens in November. And whatever that something is, we're not disabused of the idea that our spin magnitude distribution might have a little more support for larger near maximal spin magnitudes. We're not disabused of this notion even when I fold in the remaining 2 months of this latest observing run. And so the point I'd like to make is that we might actually be able to use this as another method to identify events that are kind of strongly informing our understanding of the astrophysical population. Right, so in the y-axis, in the top right, I'm again showing this distribution after each month. And in the bottom, I'm showing a marginal posterior on the variance of this population distribution. I'm showing it immediately before one particular event, GW 231123, and before is in the purple. In the dashed orange line, I'm showing immediately after I observe this particular event, and in yellow, after I fold in the rest of the new data set. Right, so, okay, so I look at this and I say this particular event, 231123, is pushing the variance to have support for slightly higher values. This is not a statistically significant difference, but it kind of stands out when you look at the PPDs and these marginals. Now, this is not actually super surprising for the gravitational wave nerds because GW 231123 is not only extremely heavy, but it has support for near maximal spin magnitudes with our current analyses. I can talk more about that particular event if you're interested, but really the point is I can see event by event what is driving my population inference, and that's kind of cool. Finally, I'd like to say that we apply this framework to simulate a simulated Mach analog of gravitational wave sources, and under the assumption of a much higher dimensional population model. Right, so in the previous slide, we were assuming all kinds of power laws and Gaussian peaks to make the functional form simple. But here, we're going to use a method which is essentially a binned Gaussian process. We're going to remove a lot of our assumptions about the shape of the gravitational wave population and see if we can still recover the correct distribution. This is, by the way, using a particular method actually developed by a lab mate of mine, this particular variation of the binned Gaussian process. But the basic idea is that I take my source parameter space, where I want to model my population distribution. Here I'm going to take primary mass and redshift, and I'm going to divide it up into evenly spaced bins, right? So I take 10 bins along the mass axis, I take 10 bins along the redshift axis, and now my goal is to infer the merger rate of black holes in each of the 100 pixels on that grid. So in the top row, I'm showing my marginal posterior on the merger rate density as a function of redshift. You can see those 10 bins. And in the bottom, I'm showing the merger rate density in log mass. We actually bin in log mass. Turns out to be a little easier, whatever. And I'm showing the marginal on the merger rate density as a function of log mass in the bottom row. In blue, I've performed this analysis with Hamiltonian Monte Carlo, again, the kind of usual thing, assuming uninformed priors. In white is the true astrophysical distribution. And the colors are performing this variational inference or Bayesian updating. So specifically in the left column, I've performed this analysis, also assuming uninformed priors with variational inference. I know this is a Bayesian updating talk, but this is cool, cool on its own because using variational inference as opposed to HMC in this high dimensional parameter space gives us like 100x speed up. So I've been trying to like wave this at the folks in our field who do similar high dimensional, flexible analyses to get them to use variational inference, and I think they're starting to listen. In the green and the pink, we also perform Bayesian updating. So in the green, I take my mock catalog and I've split it into 2 batches of data. I analyze the first batch and then use that to inform my analysis of the second batch. And in the right, I've performed this updating event by event in my mock catalog. So the key takeaway is that not only can I use variational inference to match the HMC result pretty dang well, I can split my catalog in half and get a similar result out, right? Oh, I forgot to mention, right? The solid blue line or solid like green dashed line, right? That's our median. The inner region I'm bounding is my 50% credible bound or 50% credible region, and the outer is the 90%. Okay, so I can either run variational inference on everything at once, or I can split my catalog in half and I can get the same result as HMC. That's nice. But when I perform these updates event by event, I start to see basically mode collapse in this reverse KL over many successive updates. I'm able to get the median, especially in the redshift distribution, I'm able to get the median merger rate density, but I don't get the error bars at all, and my variational approximates are a little too narrow. And so I think this is a similar story as we saw with the spin tilts. I think that this Bayesian updating is really well when I take informative enough, you don't quite know the condition for informative enough, but informative enough batches of data. But if I try to perform many updates with very subtle and unconfident features in them, those tend to wash out and I get the wrong answer. So, okay, I'll pause there again if anyone has any questions before I wrap up. Yeah.
So you mentioned earlier one of the hyperparameters is the flow, right?
Yes.
Is the size of the flow, the
Yes.
shape, like so how did you decide that? And what is like the typical shape of your posteriors, right? So
Yes.
is it bimodal? Is it what is it?
So we're pretty blessed in this particular population, like context of population inference, that everything's pretty Gaussian, at least in the 2D marginals. This is becoming less and less true with those like strongly parameterized models we looked at earlier. We're already starting to see these big shallow tails, which are really annoying. In these higher dimensional problems, as I add more and more bins, it starts to Gaussianize really nicely. So to answer your earlier question about how did we choose the flow or the particular functional form for the flow, so we in the previous work, we just looked at variational inference in this context of problems. It was just we tinkered with a bunch of things. And we found this block neural autoaggressive flow happened to work really well, especially when you paired it with a warm-up, like a cosine decay learning schedule. Okay, for whatever reason, that worked really well. And so I wanted to try and use that in this same work because we're like, okay, I'm going to at least fix this one hyperparameter to reduce the amount of tuning I need to do. I think what I learned is that I could get it to work in these high-dimensional problems with a lot of tinkering, trying a pretty big coarse but big grid of learning rates and flow sizes and so on. I could get it to work in some of these cases, but I think fundamentally I think this is the point you're getting at. This is actually a pretty Gaussian posterior, and I think the block neural autoaggressive flow is like total overkill. And so what I'm experimenting with right now is different essentially Gaussian approximations that I can use.
Yeah, I mean if you just use the multivariate Gaussian, it's even so much faster. I mean it's crazy fast. Yeah.
So I think that will be that I'm excited to do that experimentation, and we'll see how it goes. So to kind of sum up, I have no idea where I am on time.
You still have 12 minutes.
Okay, perfect.
I mean, we should include some questions, but
Perfect.
Yeah.
So I think I'll take this opportunity to summarize. So Bayesian updating, like we discussed, is a natural solution to deal with the growing size, and I didn't comment on this too much, but also the growing complexity of our gravitational wave data sets, right? We expect many orders of magnitude more data in the future, and Bayesian updating allows us to split our data into smaller, simpler parts. We put this into practice with neural variational inference for both real and simulated data sets under both these like strongly parameterized models, as well as these really flexible high dimensional population models. And they also give us some extra science goodies kind of for free. Not only do they enable us to do, hopefully, real-time updates to our population models, as well as corresponding estimates of like the rate of certain source classes, as well as estimates of significance of data as they arrive, like astrophysical significance of data as they arrive. They also allow us to identify which events are kind of strongly guiding our population inference. And as a side effect of using this variational inference, I have a really efficient representation of my population likelihood that I can combine with other downstream analyses, like certain gravitational wave cosmological analyses. But if I had to put that all into one phrase, I think I would say that Bayesian updates of our gravitational wave population models, they may be necessary in the future. I think we've demonstrated that they're possible, and they unlock some additional real-time science. So yeah, if you want to find the paper, you can find it there. You can find me at my email or my website there. Thank you so much.
Thank you, Noam. That was actually a pretty good time.
Okay.
Questions? Do we see a world in which MCMC is not needed anymore? I mean, Phil will tell me normalizing flows are overconfident. But I mean, like, let me see if I can ask a serious question. Is there an advantage to still trying to do the computationally expensive NCMC in this particular field?
I think not only advantage, but I think it might still be a necessity. But here's why. So, I outlined, like if I look at this plot, right? My dream would be that as the gravitational wave data come in, second by second, I have some super high dimensional flexible model that I'm able to update, and I can see the black hole pop in and my multi-D grid in the high dimensional parameter space. That would be awesome, but I think there's always going to be a question of like, well, how do you know your variational inference thing? Like, how do you really confidently and robustly evaluate convergence? In this example, we use essentially the importance weight distribution. We try to importance sample from our variational approximate to the target density, but that's actually a really conservative metric for convergence. On the other hand, I look at the loss curve and I say, well, it went down, but I don't know what that actually means about my target density. And so I think, kind of from the methods development side, we need a lot more understanding of like, what are our kind of robust measures of convergence that lie in the sweet spot of like strict enough, but not too strict. As well as, and on the other hand, I think it's fine if we say, I'll let this go in real time. I'll let it chug along. Maybe I can develop some metrics for when I need to stop the Bayesian update and just fit everything at once. I don't know. But, I'll let this chug along in the background. And then if I see something really interesting astrophysically, I say, okay, let's take a step back. Let's, spend a few weeks of compute analyzing the whole thing with HMC, because now we know it's worth it. That's the vision I have in my head right now, but we'll see what happens when we make contact with those data sets.
Thanks.
Yeah.
Yeah, do you see, so I think like these methods have the efficiency of that, right?
Yes.
So with a little bit of compute, you can just, you guys did this too. Do you see any way to use more compute with these methods and maybe have good enough posteriors after very, one more sample?
Yeah. So I'm going to try and answer what I think your question is, but tell me if I'm wrong. So in principle, right, we should be able to extend the same framework to, I should be able to, for example, parallelize my training over multiple GPUs if my likelihood evaluations are really expensive. I should be able to do that. Or, alternatively, I should be able to just say, hopefully I have access to a powerful enough GPU for long enough that I say, well, I've done some hyperparameter tuning. Now I'm just going to let it train for 10 or 100 times longer. I can't comment specifically on whether I will have access to that compute, but it would be nice. I think the challenge, like the personal challenge I have always had with these methods is like, you never know how long is enough, how much compute is enough to throw at it until it works. And so I think that is, a problem we can continue to explore, but does make it challenging if I just want to ask someone else in the LVK collaboration, like, hey, can I just sit on this GPU for N weeks? I don't precisely know how many N is. That's how I'd answer your question, but tell me if I went in the wrong way.
I think that was my question, and it brought me to think of another one, which
Yeah.
is, if you have a grant that is, okay, I have this GPU power for this specific estimation project.
Mhm.
And electricity is free, so you want to just leave it on.
Mhm.
And when it gets a new data point, just use as much compute as you need.
Hmm.
Do you see a way towards that?
Oh, in terms of just implementing that kind of thing? Or in terms of realistically?
How would it look like?
Mm.
I'm thinking of the curve of the beginning, just increasing the amount of data, so you just want to have this thing on.
Yeah, I think you very much could. I haven't thought in detail about what it would look like. I know there's these different active learning approaches, and they kind of take the approach of, well, what data do I need to improve my approximation of some function in some part of some space? But maybe you could take those same methods and spin it around and say, like, all right, so new data comes in, can I update? I mean, like we kind of do that, right? So as I mentioned way earlier, we're training this one guy, and it does stop at some point, but we use the trained parameters to initialize training of the next guy. I think you could imagine just discretizing in that way, basically. Yeah.
I guess one of the most basic observables that you have is how often you actually detect new gravitational wave events in terms of the population.
Mhm.
I'm not an expert, but at some point someone mentioned that these things were not being detected as often as you would have expected from the original prior.
Mhm.
Is that still a concern in the community? Like, are we detecting too few of these gravitational wave mergers for what we expected?
Let me think of the politic way.
I like politics.
So I think that assuming that the code is correct, right? Assuming that all the code and the actual just inference under the hood is correct, the result we get out is we get a Poisson mean rate, and it's got some error bars on it, and that's what we say. And I think that there have been in the past a combination of sometimes the code is not entirely correct, and sometimes people want to look at one side of those error bars but not the other. So what I would say is I don't think now it's a concern. I think now it's more of a like, well, the Poisson rate says this, but Poisson statistics tells us that we could get like two binary neutron star mergers tomorrow, right? And that could fall within the mean rate estimate, or we could not get any for the next few years, and that might also fall within the mean rate estimate. The error bars, particularly with BNS, actually are actually pretty big on one side. So, yeah.
Cool. All right, is that it? Noah will spend the rest of the day maybe at 3 or 4 by my corridor if someone wants to talk to him.
Yeah.
Other than that, thank you very much for a really nice time. Thank you, everyone.
Thanks a lot. Thanks a lot.
Nice.
Yeah. Doing okay?
Great, cool stuff. No, yeah.
Okay.
I really enjoyed the flow. Not the normalizing, but the